Bismillahirrahmanirrahim. This is the second part of the small signal model video, and this primarily will be solving exercise 4.14. Before we go on to the exercise, I'll just repeat a couple of points which we discussed in the previous video as well. I strongly encourage that you see that video, part 1 of this. Okay, we have to keep in mind that when we write capital V and capital D, that means the diode voltage, and this is DC. So both capital means it is DC. Both small, that is small v, small d, this is AC voltage. And the summation of the two is written as small and capital. So small v, capital D. So this is, you can say this is AC and this is DC. So it's a combination of AC plus DC. Okay, now what we're saying here, that there are applications in which a diode is biased to operate at a point on the forward IV curve. So this is the IV curve, and we choose a point where the diode will operate, and this is chosen by the voltage VD and the corresponding current ID. As you can see from here, if this is the circuit, voltage applied VD, which is the same as across the diode, so diode voltage is VD and current through this circuit is ID. So these 2 points will determine the operating point or the bias point. And as we have seen in the previous video, that ID or the diode current, DC current, is given by IS. IS is the saturation current or reverse saturation current, and multiplied by e raised to the power VD over VT. Now VD is the diode voltage and VT is the voltage due to temperature, which is assumed to be constant 25 millivolt, or in some book it is called 26 millivolt. Okay, now what will happen if instead of a battery we use a rectifier circuit to generate this voltage? Then, as you know, the rectifier's output have ripples, so these variations are ripples. And how do we take care of these? So for this, we'll now move into this diagram. If this ripple, actually this is the your voltage ID current and voltage VD. On this we are now superimposing this ripple, triangular shape almost. So a very small variation, and because of this there will be variation in the output current also, and we assume that this portion is linear. So the equivalent circuit now will become something like this, that the battery and the AC source, because of the ripple we are representing it with the AC source, the current will now change to I capital DT, that is the IAC DC we call. And similarly, the output voltage will also be from VD, it will now change to VAC DC. And so we can say that the output voltage VAC DC is VDC plus VAC. And correspondingly, this relation will now change. ID will become this instantaneous current, and for this voltage VD capital will now write the AC/DC voltage VD, and this can be further written like this: VD plus VD. Separating this, now this term is actually IDC term, so it could be written as this form as well. So this is just to give you an idea, and this form of the total current or total instantaneous current, or as I call it AC/DC current, This is, or this equation is called now the exponential model. And from the exponential model we'll proceed. So this was the current, instantaneous current. And now if we say that this AC variation is very, very small, such that Vd over Vt, that is this term Vd over Vt, is less than 1, then we can use the exponential expansion series, this, and where the higher powers are neglected when the value of x is very, very small. Therefore Ex is 1 plus x. Same we are applying here, that Id can be approximately written as Id, and this is 1 plus x or 1 plus Vd over Vt. So this is the approximation, or the small signal approximation. And this is valid for a signal less than 5 millivolt. And so from here we can write Id is in this form, just opening the bracket, and this is small signal model. Now we'll use these two models, the exponential models and the small signal models, in solving the next problem. Okay. Now let's talk about the problem. Consider a diode biased at 1 milliampere. Find the change in current as a result of change in the voltage by these values: 10 milli, minus 10 milli, minus 5, plus 5, and plus 10. In each case, do the calculation using the small signal model and the exponential model. So we have learned that by exponential model, the instantaneous diode current or AC/DC current is written by this formula. And for the small signal model, we had seen that the instantaneous diode current can be written by this formula. So we'll be using these two formulas. Now let the instantaneous current ID1 be for the signal VD1. So when we are applying or when the small signal is VD1, then this current is ID1, and when the small current is ID2, then the signal is VD2. So we'll apply this technique here. So from here we can write ID1 is IS. Now for VD we are writing VD1, this one. And the second equation ID2 is IS VD2 over VD, this two. So these two equations we have got here for the exponential model. And similarly for the small signal model also we have ID1 and ID2 by using these two voltages, VD1 and VD2. Okay, caution, watch VD, that is the AC/DC voltage, and the small signal or AC voltage. Now this is, here we are using the AC/DC voltage because this is AC/DC. Here we know that this part is purely AC, this part is DC, so that is why we are using the small signal voltages. So we had come up to this point. We found the exponential model, two equations for the current, and we found two equations for the small signal model. So first of all, we'll solve the right hand side or the small signal model. So change in current we can write is delta ID, the ID2 minus ID1, and plugging in the values, these values, solving, we come up to this point. And so change in the current or the instantaneous current is given by this formula, where it is now depending on the change in the AC voltage Vd. Okay, now we come to the exponential model. We had these two equations. So change in current we can write delta ID is ID2 minus ID1, and plugging in these values we come up to this point. But we cannot simplify it further to a meaningful value, so we'll adopt another approach, and that is we divide equation 2 by equation 1. So this we come here, is cancelled, and this can be written as e raised to the power Vd2 minus Vd1 over Vt. This goes up and gets subtracted, and this is delta Vd over Vt. And from here, actually this is an explanation that from here you can see these are the AC/DC terms, and by subtracting we were cancelling the DC terms, so all we left is with the AC term, so delta Vd. Okay, so from here now we can write ID2 is equal to ID1 goes on the right hand side, so we get this equation. And now we plug in this ID2 in the given equation here to get delta ID. So delta ID is ID2 minus ID1, plugging in the value of ID2. And now we take ID1 common from here, so we get this term. And ID1 is actually given, this is the initial current is, or the bias current was 1 milliampere. So it is the same as the initial diode current ID1. So we write it 1 milliampere here. So 1 don't need to write, it's just milliampere. So this is the final relation that we are getting for the exponential model. Now we'll use these two models to find the value. So I'm writing the small signal model first. This was the model that we got, and the exponential model we got is by this relation. Now from the small signal model we will do a further simplification. ID was given 1 milliampere, Vt we know is 25 millivolt. So the relation will become 1 over 25 delta Vd. So delta ID is 1 over 25 delta Vd. So we'll use this. Now these are the given values of change in voltage. So we say delta Vd is these four. We'll plug in these values. Okay, so plugging in here 1 divided by 25 and the value of delta V. So we get these four answers for the small signal model. Now the exponential model we have to do little calculations. You can see that delta Vd, if we are using this, so minus 10, and Vt is 25 millivolt, and by solving this we get this answer minus 0.331. And similarly for all other, here we are using minus 5 millivolt, plus 5 millivolt, and plus 10 millivolt. So we get these four answers. Now if you compare the answers, there is slight difference. Here it is minus 4.4, here it is minus 0.331, and similarly all others. But this may be because of the approximations that we are using here. And so this is the answer in the book. So this matches our answer, 0.4 and 0.33, similarly for the others. So I hope this gives you an understanding how you can solve this type of a problem. Thank you. Please share this video if you like it, or give me your comments how to improve. Thanks a lot.